Okay, so now how are we going to make a different choice if we happen to know the value of z sub c and we don't know the value for k? So we want to somehow use a linear regression, once again, to determine a value for k from the slope of our linear regression, determine the time constant. So the group that worked on this, how did you linearize differently in part C? Okay, so instead of distributing, you decided to start by dividing both sides by the carrying capacity ZC. Can you tell me what's behind that choice? What were you trying to do there?
We wanted to make it so we're trying to get so KT was by itself, going to be one step closer by itself.
Right. If it's this k that we're interested in knowing, if we want to make this k the slope of a linearized equation, we need to get it out of the exponent. We need to get it as much as we can by itself, and we need to get it out of the exponent. But we can't do that until we've stripped away the other arithmetic that's going on around it. And the first step is working outside of the parentheses because we're using order of operations backwards. Let's divide by that z sub c. 1 minus e to the minus kt. Okay, then what?
You subtracted 1 from both sides.
All right, ship that 1 from the right-hand side over to the left-hand side. So it becomes z over zc minus 1 is equal to minus e to the minus kt. Then what?
Then we took, we made multiplied by 1 on both sides to make positive 1.
Yeah, multiply by negative 1 on both sides. So this sign flips and that sign flips. Okay?
Then we took the natural log of both sides.
All right, there's the big guns. Take the natural log of the left-hand side, and the natural log of the right-hand side has the effect of just giving us minus kt. Minus kt. All right. And this is where I would stop. Is this where you stopped in your linearization, or did you go further? You took one more step?
Yeah.
Which was?
We divide by t.
Well,
We split up the natural log as well.
oh, okay. Let's take those two steps separately here. There was a minus over here as well. Let's move that over too. So, two different philosophies here. Mine is a little different from yours, but that doesn't necessarily make one of ours more correct than the other. The reason I would have stopped here, well, let me tell you what you might do if you stop there. If we stop here, now we have something that looks like a linearized equation with the left-hand side playing the role of our y. Here's our x. The slope of this linearized relation would be minus k. What would the intercept of this linearized relation be? What's b? What would go there? If there is no addition, then there is no addition. So if you ever end up with a linear equation that looks more like a proportionality than a linear equation, in other words, if the intercept is 0, then the intercept is 0. I mean, if that's what your linearization is telling you, then it is what it is. So if we stop there, then the next step would be to use a linear regression with these transformed variables. On the other hand, I think if I were actually a scientist working on this in the lab, I would probably do what you all did. I would probably take this next step and just solve the dang thing for k. And the reason that we can just solve the dang thing for k is we happen to know what zc is. We know the value of this parameter. It's only really when you have two unknown parameters, a slope and an intercept, that you really need to use a regression, a linearized regression. But if we happen to be able to take for granted what the value of zc is, then doing what you did is completely defensible, because then everything on the left-hand side of this equation is something we know. We can take our known value of zc, we can take values of t and z from our table of data that we collected up here, and we can use those values to compute values for k. The only thing that doesn't happen in that example is you're not always going to get the same value of k if we choose different data points, t and z, from our table up here. But maybe I should ask you that. How did you use your equation down here at the bottom to determine a value for k? What'd you do?
Oh yeah, because that was part D.
Right.
We plugged in the values for T, Z, and ZC. So what I did was well, my carrying capacity was wrong because we had messed that up. But basically for ZC, we put in the carrying capacity.
Right. If we know the carrying capacity, then we would put it in. And again, parts C and D here proceed on the assumption that we have a carrying capacity of 2,000. Now, if you use the carrying capacity from you determine in parts A and B, you're going to get a different solution here. But just for the sake of consistency, let's use the ZC that was given to us here.
Okay.
But then I guess what I'm interested in is where did your T and Z come from that you plugged into this equation?
From the points on, like I picked a point from the chart.
Okay, which one did you pick?
I picked 2 and 1.49.
Okay, so you picked a T equals 2 and Z equals 1.49. And then you get an answer from this just by plugging in. Right. And when we evaluate that, we end up getting 0.6832. 6832 for our time constant. And the units of that time constant were inverse seconds. But again, the point was that we're going to get different answers, presumably, if we choose different points from this table. And that's fine. That doesn't really matter. You can choose the point where time was equal to 2. I could choose a point where time was equal to 0. We should get similar answers as long as this model is reasonably accurate. But we're not necessarily going to get the same answers. And one of the places that linear regression, so doing it this way, is nice, is that it takes all of the points into account instead of just one of the points into account. But really, you can make the case for doing it either way in this problem. And again, what I think is interesting about K4 is the different ways of linearizing the same equation proceeding on the assumption that we happen to know values for different parameters. So when we knew the value for ZC, when we knew the value for ZC, we can linearize in the way that we linearized here, and then use a linear regression to determine the value for K. Whereas before when we knew the value for K, we could choose to linearize in a different way, Z versus e to the minus KT, and use that linear regression to find a value for ZC.